So the usual line when one introduces an invited speaker is to pick the highlights of the speaker's bio and their stellar credentials and to describe those to all of you. But Sylvie's bio is online, so if you really want to read the details and become depressed at how lame you are in comparison, you can do that on your own, I think. So, with no further ado, Energy Systems Challenges and Opportunities for ICAPS. Please join me in welcoming Sylvie Thiébaux for the first invited talk this morning.
So thanks very much, Jeremy, for this perfect introduction. All right, so the topic of my talk today is energy systems. So I'm going to try to keep you warm. I thought that I would first start by explaining why I picked up this topic. And so the reason is that in the past 5 years, even though of course I've gone on researching on planning, I've also started to investigate applications of optimization and AI to smart grids, smart buildings, and things like this. And so it turns out that there are great problems in this area and at the intersection of planning, scheduling, and control are the kind of challenges and opportunities that I see for us as a community in this area. So I should upfront warn you that I thought there was a bit of a gap, at least in practice, in the between the sort of stuff that we're doing and the needs of these applications. And so as you will see, I found myself turning more towards optimization approaches. But I don't think it's a huge gap. I think it's more, like the gap in the London metro, where you have to be mindful of it and just be prepared to make a big step if we want to have an impact in this area in the future. So why is this area so exciting right now? Well, because it's really transforming at rapid rates. And the trigger for this transformation is the availability of new technologies, in particular new renewable generation technology. So we've got large-scale generation based on solar and wind. We also have small-scale generation, so now people can generate their own power to cover their own needs, and they also can sell it to the grid to make money. And the cost of storing electricity in battery is also going down. So many of you may have batteries in their homes in the next 10 years. And well, at least here in the US, I've seen people having all of these fancy smart appliances at home that can learn, for instance, your preferences in terms of heating, which would be perfect. It would be great to have one here right now. So, the technology has really been rapidly progressing, but what's been lagging behind is the changes to the grid that would make it possible for the mass deployment of these technologies and really for them to realize their full potential. So the reason why it's lagging behind is because the changes that are necessary are really a pretty big paradigm shift in the way power systems are operated. So let me explain a bit more about that. So if you have a look at power systems right now, they follow a fairly top-down management style. So you have a few fossil fuel, coal, gas generators at the top. So when I say a few in Australia, it's a few hundreds, right? And then power gets transported to long distances by the transmission system, and then it gets distributed to customers via the distribution system. And the good thing, if anything, about these fossil fuel generators is that their output is fairly predictable and relatively easily controllable. So you can basically vary the output to make sure that the generation meets exactly the demand. And it's imperative in power system that the generation equals the demand. Otherwise, the grid becomes unstable. So in contrast, if you see what we need for the future grid, we're going to need the functions of generation and distribution to be brought in together and have a much more meshed structure on the network. We're going to have potentially millions of generators on people's roof, and these generators have intermittent output because the output depends on the weather. So it's unpredictable, it's non-controllable, and so we cannot anymore ensure that the generation is going to match the demand or follow the demand. Instead, we're going to have to ensure that the demand kind of follows the generation. And you can do this basically by incentivizing people to shift their consumption to different times. That's called demand response. The other thing you can do is store electricity, store energy, and release it when generation is low. And so that's in the context where people who used to be passive consumers of electricity now want to be, prosumers. They want to consume and produce, not only for their own needs, but also to make money by selling on the grid. A last important aspect is that currently the low-level decisions on the grid are made using a pretty clever reactive control system. And the higher level decisions are either, let's say, simple enough to be taken by humans or by systems with not too overly sophisticated level of automation. Whilst in the future grid, the situation is so much more complex that we're going to need a lot of proactive planning, scheduling, and optimization. And the decisions are going to need to be taken by computers because they're going to be much too complex to be taken by humans. So that should be music to our ears for us, planning and scheduling people. And so there are a lot of opportunities for us, but there's a number of challenges that we're going to have to overcome if we want to really make a contribution to this area. So I've listed, I think, what the main ones are. Well, firstly, the grid is a hybrid system, so we have to make discrete decisions, like which generator to start or which line to switch on and off. And these discrete decisions affect basically a physical system which is governed by physical laws that are continuous and nonlinear. So we're going to have pretty good hybrid planning and scheduling systems and the ability to integrate with optimization. The second thing is that the grid there's a lot of uncertainty. I mean, there was always uncertainty about the demand, but now there's also uncertainty about the generation because, it depends on cloud covers and wind and things like this. So we're going to need online stochastic planning and scheduling methods that can adapt to constant change and handle this uncertainty. The grid is fundamentally a distributed system. So there's many different agents and actors, and they all have their selfish, interests and preferences. You can't just, control these people or these systems directly. You have to really incentivize them, and you have to coordinate them by incentivizing them to do the right thing. And so that calls for, pretty clever distributed coordination mechanisms. And finally, the whole system is huge, right? So all of these challenges occur at really unprecedented scale. So what I'm going to do in this talk is basically take 3 problems that I've been working on to illustrate some of these challenges. So the first problem is going to be power systems reconfiguration, and I'll use it to illustrate the need to integrate planning and optimization. The second is residential demand response, and I'll use it to illustrate the need for planning under uncertainty and the type of uncertainty we have. And the third one is about distributed coordination of all of these new prosumers of electricity using, hopefully, distributed planning and scheduling. When I say distributed planning and scheduling and planning, there's a lot of optimization, right? I don't necessarily mean, the sort of planners I write. Okay. So before I start, this work, of course, has been done with many people, both students and colleagues, both from within our group and outside our group. And so this is a non-exhaustive list, and I thought I would take the opportunity to thank them before I start. All right, so the first problem I'm going to look at is power system reconfiguration. And I've picked up that problem because I think it's a perfect example of something that needs to be automated, even now. And so I'm going to talk about well, the problem briefly, then optimization approaches, and then planning approaches. So firstly, if you want to work in the field of power systems, you have to model the network. And at the level of abstraction that we're interested in, we can start by modeling it as a graph whose nodes are the network buses. So a bus is a place in the network where consumption occurs, or where generation occurs, or where two branches of the network join. So that's a bus. And then the edges of the graph are basically the electric lines that join these buses. Now, the reconfiguration problem is about finding a sequence of line switching operations. So you switch lines on and off. That is, you enable or you disable some of the edges in this graph in order to make sure that some of the buses, I mean a given set of buses, are supplied. And so you can have a range of optimization criteria that depend on the problem. So you might want to minimize line losses, you might want to balance load, you might want to reconfigure because you're going to do some maintenance on the network, and so maybe do the least possible amount of change. So that's for optimization, but you also have constraints. And again, there can be constraints that depend on the problem, but you have a core set of constraints that you must always satisfy. And they are that you cannot overload lines and generators, which have a certain capacity. And you also have to keep the voltage in the network within certain bounds, I mean, which depend on the country. And so this problem is difficult because in order to check that these constraints are satisfied, you're going to have to reason and model the propagation of the power flows. I mean, the way power flows through the network. And that is governed by physical laws like Ohm's law or Kirchhoff's law, which apply to complex numbers because it's alternating current. And when you project these laws on the real and imaginary axis, what you get is something like that. So, I mean, you don't need to understand this, but briefly, this gives you the power flowing on the line between bus I and J in both directions, and there is a real part of the power, the active power, and the imaginary part, which is the reactive power. And you express this in relation to the voltage, both the real part and imaginary parts at the buses, and some of the line parameters. And then you have Kirchhoff's law that says basically that anything that comes in at a node comes out. So you have all these equations for all of the lines and all of the buses. And then you also have the constraints that I talked about. So voltage is within bounds, generation is within bounds, and you can't exceed line capacities. So the reason why I'm showing you this is because I want you to observe that these equations are nonlinear, and they're even non-convex. So it's not going to be completely easy to solve them. And worse, once you throw in the line switching thing, for reconfiguration, then you have to introduce binary variables in the system of equations. So for each line, you're going to have a binary variable, Zij, so a line between bus I and J, which is going to be 1 if the line is on, 0 if it's off. And so you're going to say that Ohm's law, for instance, only holds if the line is on, and otherwise the powers are 0. And when you have that, you're really non-happy because you have a mixed integer non-convex problems. And the problem is that the optimization solvers that exist for these problems are still in their infancy. So it's pretty difficult to scale up. Nevertheless, you might try to use some of them to solve the reconfiguration problem. And so if you do that, you're going to do something similar to what people do in set planning. You're going to duplicate this equation, k times for k times steps, and then you're going to ask that the initial conditions are satisfied at the beginning, that the goal, so the set of buses, is fed at the end. And because it's inherently a sequential problem, you're going to ask that at most one of the switching variables change from on to off or vice versa at each step. And so the kind of solvers you might want to use to solve these problems are usually combined interior point methods, which are pretty good with power flows, with branch and bound. And because the problem is non-convex, they're not guaranteed to give you the globally optimal solution. So they're going to give you an upper bound. But there are ways to kind of mitigate that if you really want the optimal. So you can have, I mean, people have done scores of convex relaxations of these power flow equations. And people, including actually myself, have worked on how to find convex envelopes of these on-off constraints. So that would be when the line is on, when the line is off, and then you can find convex envelopes that you can use to actually have this mixed integer convexification of the problem. And with that, you can get a lower bound on the objective function, and you can compare your lower bound with the convex relaxation and your upper bound with the heuristic method, and if they match, then you're happy you found the optimal. Otherwise, there are ways that you can improve this. Now, unfortunately, even though interior point methods are really good at solving a one-shot power flow equation, so one-time step, no binary variables, so they can handle, I don't know, networks of several thousands of buses. Once you throw in the binary variables and the multiple time steps, we're stuck at, you know, a few tens of buses for reconfiguration. We cannot really scale it up. So, well, in a way, that's good news for us, AI planning people, because we can try to use planning to solve this. So, if you try to use planning to solve this problem, the first obstacle you have is that planning actions usually assume that the effects of actions are local, right? You change a few things. Whilst here, a single switching operation can actually affect the power and voltages in the entire network. That's a consequence of the power flow equations. And worse, the changes, the way these are affected, depends not only on the line you just switched, but on the position on-off of every other switch. So basically, there's no way to compactly represent this with even with conditional or universally quantified effect. So what we need instead is kind of the ability to infer possible values for these numeric variables, like the power and the voltage, from the states of the switches, like on and off, and the constraints on the state, which are captured by these power flow equations that I showed. And as you know, planners are not particularly good at handling, zillions of numeric equations. So an interesting approach to try to do this is actually to combine a planner with an external optimization solver and let the planner handle the planning bit, so the switching, and let the external solver, like the interior point method, to handle the power flow equations. And so when you do that, the question you're asking yourself is, well, what should be really the interface between the planner and the solver? And how can you inform the heuristic of the planner using information produced by the solver? So we basically produced a solution to, I'm going to explain our solution to this approach. I should say up front that we're by no means the only one working on this planner-solver combination. And so I will mention some of the other work after that. So our solution is good because it's completely general. You basically couple a planner with a solver, and the equations handled by the solver can be anything. Or they can be power flows, or they can be other numerical equations, or they don't even need to be numerical constraints. They can be any other type of constraints. So how does this work? Well, so this is how the planner and the solver communicate. First of all, we have two types of variables. We have primary variables handled by the planner, which in our case are going to be the switches that can be on and off. Then we have secondary variables handled by the solver, which in our case are going to be powers, voltages, etc. And these two are linked together by a set of on-off constraints. I should have said this is the name that the optimization people give them, on-off constraints. So the left-hand side of an on-off constraint is a conjunction of variable, value, equality over the primary variables. And the right-hand side of the on-off constraints are constraints of the type that the solver can handle, whatever that is. So in our case, they are power flow equations. So now you can see there is a neat separation between what the planner needs to know about and what the solver needs to know about. The planner doesn't need to know about the constraints and vice versa. So the operation we need to do on this is decide when a state is valid. So when does it satisfy, in our case, the power flow equation and the constraints. And so in order to do that, we basically look at which constraints are enabled, or active, sorry. So the left-hand side of the constraint is going to be either true or false in the state. And if it's true, then the right-hand side is active. So all of these are going to be active because Z12 is on here. These one are going to be inactive, and again, that one's active because Z23 is off. And so all of these other constraints are inactive. And so to ask whether our states satisfy the constraints, we basically ask the solver, is the active constraint set consistent? If yes, then the state is valid. Now, we also have actions, of course, and actions are only allowed to affect the truth value of the primary state variable. So they're basically classical effects. The precondition or the goals are not classical, however. They can have both a primary part, which is classical, and a secondary part, which is again a constraint on the secondary variables. And so to check whether an action is applicable in a state, you have a look at whether the union of the secondary precondition and the active constraints in that state are consistent. And if they are, then the action is applicable, well, especially if the resulting state is also valid. So with what I've given you here, you could basically have a blind search planner solve the problem, because you know when actions are applicable, when goals are satisfied, etc. How do we do to basically guide the search of the solver towards the goal? So we need to basically come up with an extension of heuristics that handle this external solver. And so we chose to extend the delete relaxation heuristic. So in order to understand what we do, it's best to look at, in your mind, the value accumulation semantics of the delete relaxation, where a relaxed state maps each primary variable to a set of possible values. So a switch can be either on, off, or both on and off, right? That's the delete relaxation. And so consequently, if you have a look at the left-hand side of the on-off constraints, which are a conjunction of variable value equality over the primary variable, they can also have a set of possible values. They can be true, false, or both true and false. So for instance, now these guys are going to be both true and false because Z12 is both on and off. So all of these now are true, both true and false. And we're going to say that a constraint is active in a relaxed state if false is not a possible value for the left-hand side. So now, all of these constraints are inactive in the relaxed state. And so you can see that as we're going to accumulate more and more value in the primary variables, as we progress in the relaxed plan, then the set of constraints is going to basically decrease. And so now the only thing we have to do is basically to test whether actions are applicable in a relaxed state. And again, they are if the the primary precondition can be true in the relaxed state, so as true as a possible value, and the secondary precondition plus the set of relaxed active constraints is consistent. And so once I've said this, basically I've said what I need to tell you about this constraint-aware version of the delete relaxation, because we know when to apply an action in a relaxed state. And so we have this constraint-aware version of the delete relaxation that uses constraint checking of the external solver, and with that we can build a relaxed planning graph in the classical way. and compute heuristics. So we focused on admissible heuristics, I guess partly because Patrick loves admissible heuristics and optimal planning. And so we compute, for instance, Hmax from the relaxed planning graph. We also can compute H+ using a method that we presented a few years back, which is called the iterative disjunctive action landmarks method. Because what this method needs actually is to do relaxed reachability tests for problems with subset, restricted to subset of actions. And so, so we can compute H+ by using our relaxed reachability test using planning graph. We can also similarly compute an equivalent of LM-cut. We can also compute abstraction heuristics, in particular pattern databases heuristic, by taking the pattern to be a subset of the primary variables. And so things that are not in the pattern can be basically true and false. And then we can fall back nicely on the principles we established for the delete relaxation. Right, so how does this work in practice? Well, the good news is that it works better than the MINLP solvers, at least in our experiments. So you can see here on a number of power supply restoration problems, that is reconfiguring to resupply people that were left out of power following a fault. The percentage of problems solved, cumulative percentage problem solved as a function of time by the MINLP solvers in blue. Even blind search in red does better. H+ is capable of improving things if given a modest amount of time, and then pattern databases have the greatest coverage overall. So it's kind of interesting to see H+ here pays. I mean, in the classical planning setting, it doesn't. But here, where we have a lot of overheads in computing, you know, the heuristic and even successes, then a more informed heuristic like H+ can actually pay. A good thing also is that planning can prove unsolvability of problems. So there is another 15% problems here that are unsolvable, and the planner can prove it, whilst the MINLP solver cannot because it's limited in time. So the bad news is that these problems are still pretty small. So, you know, 6 to 24 bursts, I mean, yeah, we're not going to go very far with that. So we're going to need to do much more if we want to manage to scale to those problems, at least in the optimal setting. There may be, I think in the suboptimal setting, you can do better right now. So to conclude just on this first problem, if you want to deal with power system, you have to handle power flow equations, and they're pretty complex and nasty and nonlinear. Our opportunity to do this is to couple a planner with an external constraint solver, and maybe we can even make this a mainstream optimization technology as an alternative to MINLP or even non-numerical, to handle non-numerical constraints. If you want to do this, we need to adapt heuristics, and you know, that's what I've presented is one possible approach, but we need to work at it. We also need to adapt search algorithms. So I haven't mentioned this, but the algorithm that we use on our experiments is not A*. It is a partial expansion version of A* that only generates preferred successes in the first place and only the non-preferred if you need to. And that is really crucial because, again, of the overhead of computing successes and evaluating them. If we want to play in the optimization game, we're going to need to have wider range of objective functions, like not just plan length or sum of costs, just action costs. And I'm pretty pleased to see that people are starting to work, actively on heuristic for state-dependent costs, including, I think there are some papers in this conference. So the approach that I talked about originated with the work of our PhD student, Frank Ivankovich. There are other approaches to coupling a planner and a solver, in particular the work on semantic attachments by colleagues from Freiburg and KCL. So there's a bit of differences between semantic attachment and ours. So with semantic attachment, the secondary variables value are a function of that of the primary variables. Whilst in our case, the secondary variables are only constrained by the value of the primary ones. And consequently, in our approach, the secondary variables value do not persist from state to state, while they do in semantic attachment, and that's got advantages and inconvenience. Now, there's been also heuristics for semantic attachments, so the work of Chiara Piacentini and Sarah Bernardini, where, at least in the numeric case, what they do is approximate the numeric equations into something linear or even constant increase-decrease that numeric planners can handle, and then they fall back on heuristic for numeric planning. If you like this approach of planner-solver combination, I strongly suggest you go and see Chiara Piacentini's talk this afternoon, where she's going to show you, so she's worked mostly on inadmissible heuristics, but that this approach can handle pretty nicely a range of practical problems. All right. So this first problem was dealing with the grid side of things. Now we're going to move to the demand side of things. So the demand side is the side of residential customers and buildings, where a lot of the power is being consumed. So the problem we're looking at is demand response. And basically what demand response is about, it's about incentivizing people or households at least to shift their consumption to different times of the day. And the reason for this is firstly because it reduces electricity prices on the wholesale energy market, so on the grid-wide energy market, if you like. To see this, you can have a look at this picture, where you can see in red the price of the electricity as a function of time, and in blue the demand curve on a day, I mean a summer day, but not particularly crazy, in the state of New South Wales. And so you can see this peak of price here, and it's due to the fact that the cheap generators could not ramp up fast enough to cope with the rapid increase of the demand here in the morning. And so we had to switch on more expensive generators. And so after the cheap generators caught up with the rise, then the price went down. But so if we had been able to defer some of the demand from that day to the night before, then the price wouldn't have peaked at all, right? So that's the first reason why you want to get people to shift load. The second reason, which is going to be very important as we move through to higher penetration of renewables, is that this is the only way to make sure demand matches the generation. I mean, remember, we can't control the renewable generation, so we have to control the demand. So how do you incentivize people to shift their load? Well, you pay them, right? Or you make it expensive for them not to. So basically, if you want to do a demand response, you need to have things like time of use or real-time price of electricity. And so, yeah, the price of electricity is going to vary from time to time. And the price can also depend on location. If, for instance, you're trying to balance a renewable generation with demand locally. So the problem is that if you have a real-time price of electricity in your home, you're not going to spend your time, looking at the price and deciding, should I start with my washing machine now or do it later, right? I mean, it's tedious and you're not going to do it well anyway. So for demand response, it's crucial to have energy management systems that do this for you. So this energy management system basically react to the real-time price by scheduling all the shiftable loads, so things like washing machine, dishwasher, air conditioning to some extent, hot water heating. So they schedule all of these appliances. They also, importantly, decide if you have a battery, when to charge the battery, when to discharge the battery, and when to export power on the grid, if you've got a PV or battery, and when to buy power. Right? So they're trying basically to optimize all of these decisions to basically reduce your costs without sacrificing your comfort too much. So there's a trade-off between comfort and cost, right? Some people really like, cutting their costs, and they don't mind if it's a bit little chilly like here. Although here, I don't think that's I think the problem is the opposite. They're going to pay more, and we are not particularly comfortable. But some other people basically, like their comfort, and so they're not going to be able to cut costs as much. All right, so the key issues when you're building this energy management system are pretty much twofold. First, again, you have a hybrid decision, right? When am I going to start my dishwasher? And you also have continuous decision. How much power am I going to export? The second issue is uncertainty. So there's a lot of uncertainty in this energy management problem. So you have uncertainty, first of all, about environmental condition. I mean, you can't predict what the temperature exactly is going to be, many several hours ahead, and so how much heating or cooling you're going to need. You can't predict, that's much more unpredictable, the cloud cover, and so you don't know how much irradiance you're going to have on your panel and how much it's going to produce, and you can't predict with certainty the real-time price. I mean, with certainty. The worst uncertainty is caused by the occupants of the house, right? We don't know when someone's going to go and want to drive their electric vehicle and is going to want to, find some amount of energy in this battery. Nor when they're going to want to, let's say, come back home and want to find their living room cozy. So I'm going to briefly explain how we handle these issues and build effective residential energy management systems. So sadly, what we ended up using is MIP. Basically, something simple. We have an horizon for the scheduling. We discretize. And for each devices in the house, we have a MIP model, which interestingly is very much like what you would do, for instance, with planning. So for each device, you have state variables. So for this version of, for instance, this example that can fit on a slide for a battery, you would have one state variable, which is the energy stored in the battery. Then you have action variables. It's basically what is the instantaneous charge-discharge power out of the battery. And so if it's negative, it's charge or discharge, it's positive. And then you need to update the state of the battery at a certain time step, which you do by looking at what it was at the previous time step, plus what was charged, what was discharged, multiplied by the duration of the interval, of the discrete interval. We also have to handle several types of costs. So first of all, the costs of buying power from the grid, or the negative cost of selling. Hopefully it's negative. Also costs reflecting the comfort of the occupants, and costs reflecting the wear and tear of the equipment. Like the battery, you cannot just go and charge, discharge, whenever you want, or it's gonna weigh you, kill your battery. So basically we do this for all of the devices, and we throw this at a MIP model, asking it to minimize the cost, and as I'm going to show you in a minute, it works really pretty well. So how do we handle the uncertainty in this setting? Well, we use something that's called online two-stage stochastic optimization, which I'm sure you'll be familiar with if you know optimization. So what it is that it's the online comes from the fact that it's a receding horizon control approach. So basically you schedule over a certain horizon, you execute your kind of immediate decision, and then you shift the horizon forward and you do this again. So it's like just a basic online approach. The two-stage stochastic comes from the fact that these approaches differentiate between the first stage decisions, which are really the immediate decision that you're going to make, about which there is not too much uncertainty, and the more future decisions, the second stage decision, about which there is uncertainty, and that uncertainty is handled by sampling a reasonably large number of scenarios, reflecting possible future values for the parameters that are uncertain. And basically what you optimize is the cost of the first stage decision plus the expected costs of the second stage decision over the state of scenario. I should have put an expectation. That's just expectation of the rest. And so basically what you do is that you robustify your first stage decisions, those that you're going to execute, with respect to possible futures. And the good thing is that this also can be solved as a MIP, because instead, the only change that instead of having one trajectory and one set of variables, here you duplicate the set of variables, and this stuff you can, this objective you can handle as a MIP. And it works really, really fast. So to show this, we made experiments, so 9 different set of experiments, which you see here. Each was 7 days long. The receding horizon length was 16 hours because, in fact, we figured there was not much point. Beyond that, you didn't really win. The discretization is 15 minutes, but we run this stuff, the optimization, every 5. And so we compared a number of controllers. Firstly, a naive energy management system, well, I mean a naive, someone like me in charge of energy at my home, so I don't have any ability to react to the, to respond to the real-time pricing. Then we had a smart reactive controller that uses reactive control policy that looked at the fluctuation of the price to decide what to do. Then we have an expectation online algorithm, so that's basically the deterministic version, deterministic planning or scheduling, that takes just the expected value of the uncertain parameters as input, or the most likely one for things that can't compute an expectation on. And our two-stage online controller. And we also compared with an algorithm, deterministic algorithm, that's got perfect foresight, that knows absolutely everything that the temperature, the home occupant is going to do over the 7 days. And so you can see that the cost savings, if you take the naive controller as the baseline, are much higher for the approaches that plan ahead as opposed to the reactive approach. You can also see that the two-stage online approach is, I mean, I was very surprised on how close it would get to the perfect foresight. I mean, this thing knows everything for 7 days, right? What else? You might be a bit disappointed about the small gap between the two-stage online and the expectation. But when you think about it, it's to be expected because they only really differ when something really unexpected happens. And on our 9 scenarios, it only happened once here, where the expectation online, which is the, this green thing here, had a much higher cost than the two-stage online. And that occurred because one of the occupants decided to have a shower at a very unusual time, hot shower, and there was no hot water. And basically, the controller got penalized for this, whilst the two-stage one was able to anticipate this as one of these possible scenarios. All right, so another thing you can notice is that these algorithms are extremely fast. So grand total runtime of this stuff over a day, 64 seconds. So, I mean, we're going to be struggling to beat this with planning, or the sort of planning stuff we do, but I still think there are opportunities. So the opportunities are on the one hand on the hybrid numeric planning side, and so I'm really pleased to see that there is a growing number of hybrid planners, even if they don't seem to make it to ICAPS according to the acceptance rates. I'm also pleased to see that there is a regain of interest in numeric planning, and I think it's because people realize that if you have a hybrid problem and you discretize time, you essentially end up with a numeric planning problem, and in fact the numeric planners are capable of providing a reasonably practical solution to a lot of these control planning problems. So I think one of the opportunities again is in trying to handle the nonlinear dynamics. I mean, we're not going to beat the MIP solvers. You've seen the runtime, right? Whilst nonlinear, non-convex is really hard and is needed for certain applications with batteries, air conditioning, and all that. And so I think 2 areas in which we should work there is plan validation for nonlinear dynamics, I mean, Val is limited in what it can do, and I think we can improve. Heuristics for nonlinear dynamics. I mean, so last year, Enrico Scala proposed an extension of the interval-based relaxation, which does not make any restriction about dynamics, but its informativeness could definitely be improved. And finally, the other area where we can improve, I think, is by optimization approach, is by exploiting our ability of not having to discretize time in particular. All right, so it looks like I need to move fast. One point that I want to make about uncertainty is that the uncertainty in these problems is really of the exogenous nature. I mean, it does not arise out of the actions that we execute, I mean, that the planner prescribes. So MDPs are really overkill here. And so what is more useful is the type of approach that I've mentioned, which in planning are called online anticipatory planning, and there was some interesting work in this area. Optimization in hindsight is an approximation of that. There's also plan-based policy learning approaches that generate lots of scenarios, generate deterministic plans for them, and use a classifier to learn a policy. All right, so I want to start my third problem, which of course I kept the best for the end. And so we're going to go back to the bigger vision of the smart grid, where we need to coordinate prosumers equipped with these energy management systems. And so that research is part of a project which I lead, it's called CONSORT, in collaboration with the industry partners and other universities, which is very much at the core of this smart grid vision. So remember, what is the vision of the future distribution grid? It's going to be a network of millions of prosumers equipped with PV, battery, smart appliances. And that vision is just around the corner. I mean, in Queensland, some parts have 60% renewable penetration, right? Highest in the world. The CSIRO predicts that a third of Queenslanders will have batteries in the next 10 years. And so the problem is that when you have that much capacity in the hands of prosumers, you cannot leave it uncoordinated, because if everybody comes back home and start charging their battery, the network's not going to cope. And so for it to cope, you would have to make so costly investment right now on the network that it would kind of defeat the purpose of renewables. And PV actually for PV, it's already a problem in part of Australia. And for that reason, utilities have started to forbid new PV installation at places. So we believe that it need not be that way. We believe that batteries and renewables can actually help the network and help avoiding expenses rather than creating expenses. And that the trick is really to find a win-win situation where we can use PV and batteries to simultaneously provide values to their owner and support to the network. So to basically solve network issues of voltage and capacity, which otherwise would require costly upgrades. So what we want is a mechanism whereby people can use their PV and battery at home to reduce their electricity bill and get rewarded when they support the network by exporting active or reactive power when it's needed, to solve these issues. And so we want to do this in a completely automated way by turning the network into an automatic electricity trading platform. So the two technical challenges, if you want to do that, is, well, firstly, how to optimally and in the least intrusive way possible coordinate the actions of a potentially large number of batteries owned by consumers in order to provide the support that the network needs. So this is what we're doing in this project on CONSORT. We are trialing the technology on an island called Bruny Island. This island is linked to the mainland of Tasmania by an undersea cable, which gets quite stressed when tourists move to the island during the holidays or weekends. And that forces the utility in charge of Bruny Island to bring in diesel generators onto the island. So what we want to do is basically, what we're doing is installing 40 PV and battery systems at consumer premises. They are owned by consumers, and we're going to coordinate them to reduce the use of diesel. Now, these batteries are equipped with energy management system. I mean, more like a battery controller, if you like, that manages the charge and discharge of the battery on behalf of the battery owner. And decides when it's how to react to price signals coming from the grid and exporting power if it's worth it for the battery owner. All right. So what we are doing at ANU is basically coordinating these battery controllers by passing on the right prices to incentivize the controllers in the way we need it to. So our battery coordination mechanism, what it does is basically optimally schedule batteries in such a way as to provide network support. So it's very much network aware. So it models the network and the constraints, so all the power flow equation and constraints that I've mentioned. That's why it's called network-aware coordination. But also very much consumer-aware. It respects privacy. It doesn't export tons of data outside of the house. And the controllers, as I've said, respect the preferences and the constraints of the house, of the battery owners. It's online to cope with uncertainty, and it's distributed so that we can scale to large number of batteries and large network. So very importantly, this mechanism produces real-time price signals at each bus of the network that reflect the cost of violating constraints, either network constraints or participant constraints at the network. And this real-time price signal basically creates a network support market that incentivizes the controllers to prevent these constraint violations. So basically, one of the constraints we model is the capacity of the cable, and that's going to prevent it to be violated. All right, so the way it works is that we solve multi-period optimal power flow in a distributed manner using a method called the alternating direction of multiplier method. So with this method, well, basically an optimal power flow problem is the problem of minimizing the cost of serving the network given the network and participant constraints. And multi-period is because we solve it over multiple period of time over a given horizon. And we do this again, receding horizon control. We execute the 5 first-minute decision and shift the horizon. Now, with ADMM, every participant solve their own sub-problem of this big optimization problem. So the network's going to solve the power flow equations. I mean, that's Ohm's law with the complex number. And the houses are going to solve the energy management system problem that I mentioned. And it's important to see that these participants are selfishly solving those problems. And so the ADMM method has got this multipliers thing, the dual variable, that is basically the glue that makes sure that all the solutions to the sub-problems fit together and respect the constraints. And so they support a sort of iterative negotiation process where the households, the battery controllers, are incentivized to drop their constraints or pay more, hoping other will drop conflicting constraints. And so in certain circumstances, you can prove that it converges towards the optimal solution. Pretty much the last thing I want to do is show you a demonstration of how it works on the Brittany Island network. So on the left-hand side, you're going to see the network with the batteries and the network-aware coordination. And on the right-hand side, you're going to see the network without the batteries, and you can compare the difference. The batteries are represented by these blue circles when they're charging, and the radius of the circle is proportional to the charge, and they're red circles when they're discharging. Here you're going to see this little red dot is a diesel generator, and when it generates, you're going to see a big red circle. So at the beginning, it's 4 a.m., so the batteries are charging from the grid because there's no sun, right? And they're anticipating the peak of power, which is going to happen now at 7 a.m. And you can see on the right-hand side, 8 a.m., sorry, right-hand side, the diesel is going to start, whilst here, some of the batteries are discharging and completely removing the need for diesel. Now we're later during the day, and the batteries are charging from the sun this time. And again, they're preparing for the peak that's going to happen around 5 p.m. And so the gradient that you have here shows the voltage. If it's dark blue, means the voltage is low on the network, it's getting low. All right, so here is the peak. And here you can see that we cannot oh, crap. We cannot remove all of the diesel. Are we done? I put it too late. Yeah, we cannot remove all of the diesel, but we can substantially reduce it. And you can also see that some of the batteries are discharging much more than others, although it was more obvious a bit earlier, sorry, which occurs because there is a phase imbalance on the network, and so one phase is much more constrained than others, so some of these batteries need to be much more active. All right, so I'm Jeremy, I'm concluding. So with that, we can reduce 90% of the diesel, and it converges nicely way below 5 minutes within 1% of the optimal. In fact, the main bottleneck is communication speed on the island to pass on the price. Well, I was going to say that I was going to crowdsource the end of my talk, because I wanted to talk about more multi-agent planning and scheduling and what it can do for these problems, but I realized I have not been really capable of catching up with the speed at which this has been developing over the past 5 years. So I've noticed that there's a lot of work. Well, there used to be a lot of work at ICAPS, because now apparently in distributed planning it doesn't get accepted either, or doesn't even get submitted. There is work scaling up multi-agent MDPs. There's lots of work in the AMAS community, but I'm really surprised, I mean, basically at the intersection of energy and multi-agent systems, but I'm very surprised that it doesn't seem to want to model the power flows in the network. So it assumes that you can ship, packets of energy across the network without having to cope with the constraints. So quite honestly, I think once we have a high level of penetration on the network, this approach won't work. And so my conclusion slide is that I think planning and scheduling is really central to the transformation of energy systems. We have an opportunity to make an impact in this area if we address these issues. And I'm guessing that some of these issues also exist in very important areas like robotics. And so we're going to have to handle them anyway. And so on this, I'm looking forward to Manuela's talk tomorrow.